Okay guys, I back again after this break, and thanks. I think my computer now in much better shape, so I should be able to do the rest of this tutorial. Sorry for that. I think it was for my own benefit, so I got my nice coffee. Without coffee I will be dead long time ago. Trust me, trust me on that. Okay, so the last thing we did is to make connected component in the subgraph, and we just got that, and you should be able to see. Oh, there is nobody watching. Hello guys, where are you? Okay, do I need to wait for a few seconds before I start? Come on, why it is difficult today? Why it is difficult? All right, we went home. Martin, stay, don't go. Now, did you do the first three things? Did you represent the three graphs, guys? I can't believe I could start any live tutorial without the Pareto video. Do I need to put the video again, guys? Do you think? Or we should be able just to work without it? Okay. Now, so we did the subcomponent thing, and now I want to find out the cute vertices and the cute edges in a graph. Now let me ask my assistant to write this code for me because I am super lazy to type. So I will create now a graph, which is a Lollipop graph, and I will show it. And then I will try to print a few things about this graph. The first thing I will do is just to do some print statement about this graph. So basically I want just to make it look really nice and beautiful. And this is what I will do. So now I just need to go back and start the typing. So the first thing I will do is to create a cute vertex for a Lollipop graph. Can you see the sublime? Now this is the most important thing. And now I want to do a print summary, and then I will print test is one acute vertex, and so on. So all of that should happen inside Sage. You can see the text, guys. Can you see the code, or you can't? You can. Yes, you can, which is good. Now the next thing I will do is to print all of that detail should be printed in Sage. Now I wait for my agent to finish typing. Hopefully he could type and not being a lazy guy today. So the first thing I did is to print test. Oh my god, I have to start again. I should not click there. I should not click there. That's now a miss. A big one. Okay, now this is my cute vertex code, and just go here and do my cute vertex code again. Now let me just delete that, guys. Just let me delete that for a moment, okay? And I will start again, so you don't get confused as I am now, feeling super confused. Okay, all good. Now it is printing and you should be able to see the code. It is working. It was working with me last tutorial with the cloud computing, guys. It worked perfectly. Like today, it's just only more coffee, more cigarette, and we will be all fine. Okay, that's my channel. So here I do the summary and then I print star star just align. Then I will do a test. The first test is vertex 1 acute vertex? To do that, I just do x dot is acute vertex and then I pass the name of the vertex. Now then we do test by whether the acute vertex 3 is acute vertex 4 is acute vertex 5, and then we will test the edges. So we'll take them edge by edge. The first thing we will do is test whether the edge 0 1 is acute edge, and then we'll do 0 2 0 3 1 2 and 1 3 2 3 and 3 4, and finally we will do 4 and 5. Alright, so this is my code for writing the acute vertex. Just copy that and paste it here. Now this should not be here, to be honest with you. I don't think it should be here, but because I clicked somewhere in that, it just happened. So what I will do now is just delete all of this code and backspace, all good. Now I run my script. You see, when Sage give you this star means it's running. It's just running things at the background, so you have to be a little bit patient. Okay, so this is the Lollipop graph where we have now a summary. Is 1 acute vertex, which is false, is 2 acute vertex, which is false, and is a 3 acute vertex, which is true, and which is 4 acute vertex, true. Now is 5 acute vertex false, definitely, because this is basically a vertex where we have one end, where there is one path going to this vertex, and we call it pendant vertex or a leaf. Now we need to test the edges. So the first test between 0 1 0 1 edge is not acute edge, because if you remove it, the graph will still be connected graph. The connectedness of this graph is not going to be affected if I just remove the acute vertex. Now is 0 2 acute edge? No, because also if I delete it, nothing will happen. 0 3 1 2. Now 1 3 2 3. Now the acute vertices are 3 and 4, the edge 3 to 4 and the edge 4 to 5. Now if you go and delete this edge, you just delete it. Once you delete this, 4 and 5 will be totally isolated and subgraph from the rest of the graph, and this will make this graph not fully or strongly connected. So this is what we did for acute vertices. Do you need to take time to type all of that, guys, or you just copy it and paste it from the GitHub? Let me know in the chat box, please, before I start doing the next task, which is a little bit about isomorphism. I know from the lab in the last time we did, the physical lab we did, the extra optional task was a little bit hard for you to judge whether it is an isomorphic or not. So I wrote a script just to take you step by step how we represent this graph, what we are going to test, and as well, next week lab, we will use path in order to verify whether two graphs are isomorphic or not. So do you need time or I go ahead? Let me know. CMP. Okay, now just copy it and paste it though. It's a very nice script to start with and to learn a lot how we can represent the graph in a better way. So let me now just ask my agent to type the extra task of isomorphism. So a comment, which is a comment just to write in Python that this is an auxiliary task for lab 4, and this is to represent the graph G. Do you want me to show you the graph G and H from lab 1, which is what we call it now lab 1, which is the first lab we did last time? So now, just in a few seconds, when this guy finished typing, I will show you the two graphs. So what we have the first graph, which is G, and it is a directed graph, and I use here a method called G.relabel because I feel much easier to just add them as edge by edge, and much easier not to keep typing things again and again, and not to be confused, by the way, which is here you can, by doing the add edge and remove edge, it's much easier for you now to verify, to modify the graph, rather than just putting everything in one single statement. So I finished now the presentation of graph G and the graph H, and now I will start to do the checklist one by one. First, let me print the graph. Now let me print a summary about this graph so I can see exactly what's going on. So I want to see the total number, the sum of the edges, and then I will see the total degree in the graph, which is the sum of all degree, every single vertex. I calculate the degree and then I do the sum of it. And thanks to the function sum and thanks to the function g.degree, which is going to save me a lot of time. Then I will print the adjacency matrix, and then I will print another summary about graph H. Now, when we execute this script, you will see how handy all this information. Yes, it might take you time to type it or to configure it to suit your needs, but you will find it really useful to use, and that's why I put it in GitHub so you can pull it at any time and just modify it. Alright, so then we will check whether the adjacency matrix equal in the graph A and B. This should be G and H. And then we will do G.adjacency matrix equal H.adjacency matrix. And by the way, the equal of the matrix to verify that two graphs are isomorphic or not using adjacency matrix is much more difficult than we just make the equalization sign. For the moment, for this course, it's enough for us just to say adjacency matrix 1 equal, or the adjacency matrix of a graph H is equal the adjacency matrix of a graph G. Otherwise, to be like in a very advanced way, and maybe it's a right time for me just to give you a warning. Like there is lots of YouTube videos about graph theory in specifically in this. Like in this specific case where you are using a graph isomorphism using adjacency matrix. Now some of the video they are explaining a very complicated mathematical theory. I think it's for master and PhD student in somebody who's doing his master or PhD in math, not in computer science even, because as a computer science what we are interested more in is the structure similarity between the two graphs. Now per se, just like to explain what I'm talking about, to verify whether two graphs using adjacency matrix, you have to find a matrix permutation, and then you multiply the matrix permutation by the first adjacency matrix of graph G in order, or it should give you the adjacency matrix of a graph H, which I believe this is more than what we need as a second year student doing a bachelor degree in computer information system. Okay, so be careful when you go and see those videos. They are very beautiful, they are very useful, but sometimes the knowledge given to them are more oriented to mathematical student, not to computer science. This is what I want to say, and it's a very high degree, if you would like to call it. So be careful when you see those videos, don't freak out. We don't need all of that complicated stuff to be involved. And while I'm reading about this, it's very complicated task to find that two adjacency matrices are similar without doing matrix permutation, transformation, and then you have to introduce something which is called the graph similarity. And this is like a very advanced topic in computer science. We are using this in data analytics, for example, to find or to, I'm using this as an experiment in my research, for example, to see the behavioral pattern of the user. So I record the user behavior as a vector, as a matrix, and then I make a similarity check between the future behavior and the existing behavior in the historic data. So it is something you have to be careful about. Don't go that deep. Just stick with the checklist I told you about. Check the number of vertices, check the number of edges, and then check whether the two graphs are isomorphic or not, whether there is similarity or unsimilarity. Then we will use path in order to do all of that. Okay? So be careful, just to let you know. Now my fancy script has been finished. I should be able now just to run it. All right, so I am good to go. Okay, so this is the first graph, which is graph G. And it is a directed graph, so the total number of edges are 9, and the degree in the graph, the sum of all degree is 18, and the adjacency matrix is going to be printed below, and the graph H is also look like this. So now I will have the summary, which is basically, it's telling me the total number of edges in graph H as also 9, and the total degree is 18, and this is match what I have in above. So there is like a very nice information, let me say primary information I got about the two graphs, which sound to be perfect. And we will check now, are the adjacency matrix of the two graphs are equal? So it's telling me that G and H are the adjacency matrix equal in the graph G and H. Now let me check, the number of edges in G and H are equal, it's true. Let me check, the number of edges in G and H are equal. Are the vertex in G and H are also equal? And the number of degree in each vertex. And this is the most important one that we are going to use in next lab, because once you print the path for the path, all paths, like there is a method I will show you now to print all the paths for the graph, and you will do this following. U1 degree 3. Now V1 degree is a 3. V2 is a 3, and you'll see now there is a similarity between both a graph. So yes, with confidence we can say graph G and graph H are isomorphic. So this is what I want to say. Now if you would like to print all paths for graph G and H, all you need to do is just to put like, now let me check how I declare them. Yes, G and H. Okay, so now if I want to check all the paths, and this is very important for our next lab, which is going to be about Euler circuit and Hamilton circuit and Euler path. Just type in G.all paths, and this will be take exactly 3 arguments. I forget what is this all about, so I have to just put all and and then a question mark, just to remind me what I am doing. Okay, now just let me quickly, what I do, I think I need to have a for loop. Just let me check. Start and end. Yeah. I have to do the start and the end of each vertex. So if I have to specify, for example, that I want to check U1 and the ending vertex that was U6. Okay, so this is my first one. And then I will go from G, all available paths for, and you can use the path iterator in a for loop, guys, just to check every single vertex in the graph. And this is going to be V1 to V2, and this is should print all the available path in this graph. Now let me close this. V6. We want, now he's complaining about me. Save the state of the neighbor accessor. So just let me go back to the graph. Actually, if I go V1 to V6, V2, V5, V4, then V1 again. I would say that V1 to V4 is much better to check. V1 to V4. Alright, so this is going to be it's not G, it's H. Sorry guys for that. It's just not a good day. More coffee, I will be fine. Okay. So here you have like V1 and V6, because if you see in the graph, the path is actually V1 to V6 and you go nowhere from that. But I could possibly check the other way. What if I start at V6 and I want to end at V6 again? Is it possible? I don't think it is, but just for curiosity, let me do that. V6 to V6. It's V6 only. Well, there is no loop, which is not, I don't think that's correct answer. Okay, now if I put my ending point as a V1, you will see that V6, then I go to the V3, then I go to V2, from V5 to V4 to V1. That's the first possible path. Now the second possible path, I could go V6. I wish to see now, let me try it just to see the graph and the paths again. Wait. I will print graph G again so you can see it while I'm talking about it. God, I am so lazy to type h.show. What's wrong with me today? I feel like John Oliver on the Late Show. Okay, so that's the graph. So all possible paths, I want to execute this. Wow, like I can't believe what's happening today. Whether I am so fast or my computer is so stupid. A new cell, and this is what I am doing. Okay, so the first possible path is V6. Where is V6 now? V6 to V3, and from V3, can you see my mouse? Yeah, you do. V2, and then to V5, and then to V4, and then to V1, and I will end up in here in V6, which is basically a circuit. Now also there is another path possible in this graph. So this is going to list all possible paths in the graph. So I will go from V6 to V3, from V3 I could go to V2, and from V2 I could go to V4. Straight away I could go to V4, and then I go to V1, and this is going to basically complete the path for me in this graph. And also you could do V1, V6 to V5, and from V5 you just go straight away to V4 and then to V1. I believe, yeah, there is like a huge lag today. So that's what I want to say for today, guys. Now we will start to open the session for Q&A, because in the last video I was like typing and then, oh yeah, you can do this. So it was like so much distraction for me and for the viewers and the audience. So we'll start the Q&A. If you have a question, please answer me. And don't answer me why everything is going haywire today, because I have no clue. I have no idea. Okay, so I will start taking the questions if you have any question. All right, so I have a screen here, so I need to find it. I think, yeah. I have ordered the laptop since 4 weeks. I supposed to get the new MacBook, but never arrived. Like, I don't know, they just made a new laptop for me. I can't understand why it takes 4 weeks just to order a machine in this place. Any question, guys? Because I think that's what I'm going to do for today, and I should be able to leave you go and do that, enjoy doing that script, the long one, later. Do we have to do why the syntax mark? Which syntax error? No, first of all, I think you should do it, Martin, if you want to understand the concept of connectivity and isomorphism. I would say do it. If you are lazy enough, just copy and paste, but just run it. Make sure you run and you see what's going on. Now for Mark was like, what is the error in the Irish map? Update their path. I did update the path. Did I? No, I think this is the one. If you go to the Irish map and just check, I think this is the one. I did the graph while I'm looking to the map, so yeah, because I put Carlo in the other way, maybe. Yeah, I should transform it. So this is the Irish map. So this is the N7. So you go from Dublin to Naas. This is the M7, and then you go to Newbridge, Kildare, and so on, Portlaoise, and from Naas you could possibly go to what that area? I forget. What's it called? Carlo. Yeah, to Carlo. So I assume, I assume that there is a path directly from M9 to Carlo. Yeah, there is a little road here you need to take, but that's fine. Just for representation. If you do want to see this in transformation, I would say, that's interesting. You need to check if the graph plot supports 3D, and you just transform it, or you just do it in the old-fashioned way. Maybe just do g.show 3D. And that's it. The Lollipop code, it should be in GitHub. If it's not, do I need to put it? Let me know. It should be there in GitHub. I could check now just quickly while you are here. My laptop is so slow. It's damn slow today. I don't know what's going on. Maybe I'm running too much software. look how much it takes to go to GitHub. Like, unbelievable. Maybe the network is not fine. Martin. What do you mean by the CA, the assignment? Sean, is it this the assignment? Or just lab 1? If it is the assignment, yes. And as long there is as long the assignment or due date is still open, you could do so. You could just update your submission. No need to submit a one which is not really good if you believe so. GitHub, and we will go to GitHub. Hopefully it will know my that's Chrome, not Safari. Okay, that's here. Microsoft update. That was the problem all the time. Come on. Like, why Microsoft, they never did a good software in their life? G is connected. That's an issue. Okay, so I will try to see if we can just fix that, because there's so many type for this statement here. And let me just make a comment here so you know what I'm doing. This is to check components, connected components. All right, and then that's the Lollipop. No, it's not. So let me just quickly paste it. That's the one we want. That's the one. Interesting. Looks like how it's represented in 3D, which is a strange representation. That's the one you need. George, I think George was asking about that. So guys, now this will be updated in no second. Just pull a new version of the GitHub. I'm assuming you do know how to use GitHub, pull and push and so on. Okay. Now that's here should be, and that's the Lollipop. Okay. I wish my cloud computing student they never see me doing the git and update using the web interface, because I always enforce them to use the command line. Okay, update to and commit. Back to you guys. So 10 people start to use it, and the software was good. I have to go, Basil, cheers. Okay, Martin, go if you want, guys. If you don't have any question, that's all I'm going to do for today. You have the script there available. Just read that script, execute it, and let me know if you face any issue or any problem. And I will see about next week if we will have a physical lab or a physical tutorial, or it will be a live tutorial. In the meanwhile, all I want from you guys is just go back and check all paths in the graph. And sorry for the distraction today. I will see if the video is it needs any editing or any issue I need to fix before I put it back in the YouTube channel. Thanks for joining me, and see you in the next one. Bye bye guys.